recording, and now we are recording. Okay, so what did we do? Well, we talked about time series. So a time series is what? Well, it's at the same time as data set and a mathematical model. So it's a data set of random variables indexed in time, which are obtained from repeated observations of the same phenomenon, but over time as time is passing. So the typical example of a time series is the how popular is Donald Trump time series, which measures in real time how the different polls in the United States rate the popularity of Mr. Trump, and you see that you have a curve going up and down according to the popularity of Mr. Trump at the time. And the evolution of this curve reflects various events that are occurring in the United States. So for example, you see that when he announced that he was sick, his popularity actually goes up, and so on. So it's a collection of data, but it's also a mathematical model which describes the data. So it's a collection of random variables which are aggregated in what we call a stochastic process. So we need tools to deal with the two at the same time. And one of the tools is data visualization. Wait, I just have a small worry that you're not all in the... No, you're all there. Where are you? I've lost you, sorry. Okay, so we need the tools to visualize the data. You're lucky that you're living in an era of R code, so you can just, or R software, or if you prefer Python or something else, you can visualize quite easily by using the basic visualization tools. I will do everything in R, you do whatever you want in whatever language you want. And now, well, the whole course is devoted to a very specific family of models for this kind of data. I will try to steer away as far as possible from politics as I can, so I will not be discussing the election of any election results or that kind of stuff. That's too difficult. So we'll be just looking at the maths. So what did we have to say? So all that is just some more things. So in order to be able to describe a time series, we need some vocabulary. So we need the notion of a stochastic process. A stochastic process is nothing but a collection of random variables living in the same space with a family of distributions which are related through the evolution of time. And there's many ways of giving yourself time series models. For example, you can construct them by saying, well, I take an ID sequence, random walk, or something like this. So here were a few different ways of constructing stochastic time series models, which we covered in detail last week. And one of the most important building blocks of the process, of the whole theory, is the so-called white noise, which is just a collection of random variables indexed in the correct index set. So here we have the index set, which is the set of integers, so positive and negative integers. But a white noise is just a collection of random variables which have fixed variance, fixed mean, and which are uncorrelated. So not independent, but uncorrelated. Of course, the classical example would be a sequence of IID normal random variables, but that's a very specific kind of white noise, and we will prefer to keep it general because it's not useful to do the theory only for the jointly Gaussian case. It's just as easy to do it in the general case, and anything that will be true here will also be true here, whereas it's not true the other way around, because of course not all random variables are Gaussian, and even not all interesting white noise sequences are independent. And as you know, that's something important that you should all know, but I will repeat it once more, and I repeat it a few times. Correlation is not, so nullity of correlation is not equivalent to independence. That is only true when you have joint Gaussianity. Okay, so we had defined white noise, and we'd also defined another very important process, which was the Gaussian process. And the process is Gaussian if and only if any linear combination of any sequence, any linear combination of any vector extracted from the process is itself Gaussian. And two important families of distributions of two important functions that could be associated to a Gaussian process are the mean function and the covariance function, which will then describe the distribution itself. And then there was a theorem which we will be more or less proving today, which says that, well, if you give me, so of course if you give me a Gaussian process, I have a mean and I have a covariance. But what it also says is that if you give me a covariance function, then there exists a Gaussian process which has exactly this mean and this covariance function. So that's not, in French we would say anodin. That's not a detail, because it's actually quite a complicated question. It's when does a given stochastic process exist? And that was the end of last week. It was probably a bit too complicated for some of you, but again, don't worry too much. It's just this section here, section 133, gives us sufficient conditions for the existence of a stochastic process. Even if you think about it, nothing guarantees the existence of an IID sequence of white noise. Nothing guarantees this. So in order to be able to do this, we need to have some conditions on the collection of random variables that we're looking at. And the condition is actually very easy. We will say that, so how do you describe the distribution of a stochastic process? Well, let's go back to one dimension. How do you describe the distribution of a random variable? You look at its cumulative distribution function. The cumulative distribution function is a function which associates to x the probability that x is less than x. In French, it's what's called the fonction de répartition. You must have all studied this at some point in time in your careers, so you must all know about the fonction de répartition. It's one very efficient way of describing the law of a random variable. Well, the same kind of thing exists for a stochastic process, and it's called the finite dimensional distributions. It's the collection of all CDFs associated to any collection of indices, so any t, and then associated to any, so it's a collection of CDFs, cumulative distribution functions, associated to any collection of time points t1 to tn. So it's for any, so you have a stochastic process, then you look for any n, for any t1 to tn, you look at the functions ft. This gives you a gigantic family of functions, which are called the FDDs of a stochastic process. So maybe I'll do this example again just to make sure that you're all at ease with this. So we are on page 22. Page 22. If your process xt, sorry, no bar here. If you have xt with t in z, which is an IID process, so I remind you, IID means independent and identically distributed. I hope everybody knows this. Then the FDD, the associated FDD that's what FDD is, the collection of functions which are given, well, it's ft of x. So I put a bar here and a bar there to indicate that t is the collection. So for all t, which is t1 to tn, of functions which do what? Well, which send an x in Rn. So maybe I should be even more detailed. So it's for all n, for all t, of functions which send x in Rn onto ft of x, which is what? Well, which is this. So that's just a definition of an FDD. But because we have IID-ness of the random variables, we know that this is equal to, so that's because it's IID, it's just equal to P of, how would I write it? Yeah, so let's take xt1 less than x1 multiplied by this. So, oh, sorry, I'm being, this is going to be better like this. And that's what? Well, that's the product for I going from 1 to n of the f's of xi's, where f is the common CDF of the xi's. Well, of the xti's, sorry. So, is that okay with everybody, what I've just done here?
Yes.
Okay, great, thank you. So, because I think I was a bit, so I must have told you already, you are my 6th hour of teaching today. So I'm, when I reach you, I'm barely coherent, and when I'm finished with you, I'm basically completely out of this world. I have no idea who I am nor what my name is. So I think I don't have the impression I was very clear at the end of last week, so I'll try to recover this time. Don't worry, it's nearly finished. In 2 weeks I'll just be teaching you, so that will be much easier. It's just for the first few weeks it's a bit of a rush. So let's have an example. Let's say I take f of x. So I take this guy, f of x is 1 minus exponential of minus x for x greater than 0. Well, if I give myself that function, I know that this is the CDF of an exponential random variable. And then I know that the corresponding FDD given by what? Well, given by which gives what? Well, which gives x in Rn is sent onto the product for I going from 1 to n of the f of xi's. No. The corresponding FDD, which would be given by this, is the FDD of what? Well, of the sequence xt, t in z, which would be IID exponential with parameter 1. So if I give myself this function here, I can construct explicitly the sequence which has this FDD. I just have to take exponential 1 random variables, and I know how to construct exponential 1 random variables. But in general, how do I know that an FDD... So with this here, and more generally with this here, well, I know that if I can construct a random variable with this CDF, then I can construct the corresponding IID process because I have its FDD, which gives me its existence. Now, more generally, how do I know that a given family of finite dimensional distributions is indeed the FDD of a stochastic process? Well, if we're not in such a simple case, it's really a complicated question, which is answered by Kolmogorov existence theorem, which says what? Well, which says the following: it is enough that if we take any limit of any component going to infinity, we are still left with the family at one time point less. Well, it's enough to have this condition to have the guarantee that you can construct a big enough probability space for the existence of a stochastic process with this FDD as a distribution. So basically it says that we have a very simple condition for the construction and guaranteed existence of stochastic processes with given properties. Okay? So that's basically where we had ended last week. And now we want to continue with this and study these objects in a little more detail. Questions so far?
Not for me.
Okay, so now we have a family of FDDs. We have a stochastic process, xt. It has an FDD, ft. And one of the major definitions of this, in order for our theory to make sense, we want to study the properties of these objects. As we said many times, we do not dispose of a lot of data. We have one realization, only one. So we want to make some assumptions which will allow us to say things which make sense about the behavior of this process. And one of the basic assumptions that we're going to make is that possibly after some transformations, so after getting rid of non-random parts, so what we talked about last week, so after getting rid of a certain linear trend, for example, after getting rid of certain seasonality, which we can extract from the data, we are left with a random process. And we will say that this random process is strictly stationary if its FDDs do not change over time. So that's what I mean by this, is that if I look at the CDF of any joint xt1 up to xtn, it doesn't matter if I look at time t1 or if I look at time t1 plus any translation in time t1 plus h. So maybe I'll make this a bit clearer if I look, so we're on page how much? Page 25. xt is strictly stationary. It tells you what? Well, it tells you well, first of all, it tells you that the marginals do not depend on the time. So this is, I've just taken identity, I'll call this star. I've just taken star at n is equal to 1. So if your process is stationary, well, all the marginals will be the same. But as we said already, the marginals are in no way a complete description of the behavior of the process. And strict stationarity also says that we can do the same thing at n equals 2. So we'd have that this is also time invariant. So this is also the same as this. For all h. So that all bivariate joint distributions are the same, etc., etc., etc. If I take the definition at n is equal to 3, I get that all trivariate distributions are the same, well, are time invariant, and so on. So strict stationarity is very strong. It says that whatever you look at, in whatever direction you look at, if you take a marginal, dimension 1, 2, 3, n is arbitrary, any margin that you can take will be time shift invariant. Okay, so in particular, so this will play a role later on. In particular, well, because all the marginals are the same, well, all the means are the same. So expectation of xt is equal to expectation of xs for all st. Therefore, the mean is constant over time. So it tells you that your process is, if your process is stationary, it can have a non-zero mean, but it will be evolving constantly around this mean, like that. Secondly, it tells you also that the covariance between any two, so covariance of xs and xt, is what? Well, it's the covariance of xt plus h, xs plus h for all h, and in particular, it's also the covariance of x0 and so s minus t, and it's also the covariance of xt minus s and x0. So to go here, I take h is minus t, and to go there, and to go here, I just take h is equal to minus s. So it tells us what? It tells us that this guy here is just a function of, it's just a function of, it's the same of s minus t or t minus s, so it's just a function of the absolute value of the difference between the time points at which you're looking. So if your process is strict stationary, the mean function is constant over time, and what we will soon be calling the covariance function is only dependent on the difference between the time points at which you're looking. Is this clear so far?
Yeah.
Okay.
Yes.
So that's strict stationarity. An example of a strict stationary sequence is an IID sequence. Well, yeah, I think that's actually quite obvious. So if xt is IID, then it is strict stationarity, strictly stationary. Somebody has his microphone on.
Oh, my bad, sorry.
Okay, no problem. You're of course allowed to have your microphone on, it's just you want it to be done on purpose, not by accident. So if you have an IID sequence, then it is strictly stationary. Well, that's a bit trivial, because if your sequence is stationary, ft of x is just a product for I going from 1 to n of, let's say, f. Sorry. Wait, I'll do this a bit slower. So if you have a sequence which is IID, then it is strictly, so let's say it's IID with common CDF f, then what? Well, then the probability that xt1 less than x1, I go like this, xtn less than xn, we know that it is equal to simply f of x1 multiplied by f of x2 multiplied by f of xn, which, I mean, this guy does not depend on t. So this is the same thing as this. I mean, I think I'm doing some overkill here. I mean, it's obvious. If you have an IID sequence, then it necessarily is strictly stationary. Another example, which is also trivial but will also be useful, is if you take xt is equal to x for all t, and let's say x has a distribution f, well, then that is strictly stationary because nothing depends on t. Okay. Oops. So I guess that's okay for everybody. This is a useful result which we do not prove because it's complicated to prove, but it's very useful. Well, I reformed it. It's not complicated to prove, it's just it needs a lot of vocabulary, which we're not going to do. So it just says that if you have a strictly stationary sequence, and if you have any measurable function of this strictly stationary sequence, well then if you make this into a process, you have again a strictly stationary. So you cannot lose strict stationarity by taking functions of your process. So that's quite handy because it means that anything that you define from an IID sequence, as long as you use a function which does not use the time, so as long as you have a function here which is itself time invariant, well then you maintain the strict stationarity. So for example, any linear process in some IID noise, so something like this, if it converges in a specific sense, which will be made clear next week, then the process is strictly stationary. Okay so far? I guess it is. So for those of you who are not at ease with the maths, or are not so at ease with the maths, well, you can basically look at this slide and, well, no, actually, this slide is actually quite easy. So you're not supposed to, this should not be hard. What you can look at is, you must understand this statement, but really don't worry about the proof, and we won't really be needing that statement in the sequence. But so that statement, just remember that it gives us sufficient condition for existence of a process with a given FDD. Okay. Now let's go back to more practical things that you will be needing quite a lot, but not only in the course of this course, but also more generally. It's something which is basically the center of all interest in this kind of models. It's the so-called mean, covariance, and stationarity, but weak stationarity in this case. So as we said, the FDDs completely describe the sequence, and they are the things you want. You want those in order to study your process. But in general, they are not available. In general, they cannot be written. They cannot even be accessed. They cannot be studied in any way. It's hopeless. So describing the FDDs is basically, in general, completely hopeless, unless you have an IID, or in a non-trivial case, unless you have a jointly normal, so if you have a normal process, or you have a Levy process, or you have something which gives you detailed info on the process. But in general, they are inaccessible. So what do you do when you don't have access to the complete distribution? Well, you summarize it. And what do you summarize it with? Well, the first order approximations of your distribution are, well, the mean and the variance, of course, at least for random variables. So here, because we have a process, well, the first approximations will be the mean function and the covariance function. So what's the mean function? Well, the mean function is nothing else than mu t, which looks at the expectation of xt as a function of t. This function here, it depends only on the marginal CDF of xt, because it's you're just looking at the process at one fixed time point t. So let's have a look at a few examples. So example 1.30. So now the computations I'm going to be doing are supposed to be quite easy. So we take ZT, which is white noise with fixed mean mu and fixed variance sigma squared. And we know that the ZT have covariance which is 0. That's the definition of the white noise. Then the first point, we look at xt, which is a moving average of ZT. Well, then the mean function of this guy, that's just the expectation of xt. And that expectation, it's a mu plus b mu plus c mu, because zt is white noise, so all these guys have the same mean. And that has a what? Well, it tells us that we have a plus b plus c mu. So I literally would not understand that you find this complicated. So if you find this complicated, please send me an email in private, and we need to talk. Okay? Second statement, if we have a random walk with drift, so we take the process constructed in this way, so that's the random walk with drift, the random walk built on the ZTs. Well, again, the mean function, so once again, I'm very sorry, what I'm saying might be a bit blunt, but I'm quite sincere. This should not be in any way a problem. If it is a problem, you're going to have a problem with the rest of the class. I mean, you're going to have a major problem with the rest of the class. So please give me a shout if you have a problem with what I'm writing here. I hope it's correct what I'm writing. Okay. And the last example is the cosine wave from figure 1.8. What was that again? Figure 1.8. So I took what did I take? Oh yeah, here it is. I took so xt was 2 cosine of 2 pi t divided by 50 plus 0.6 pi plus some noise. And then if I look at the mean function of this guy, well, then the mean of this guy is this. I mean, this is basically. Oh yeah, but my noise had mean 0. So this is just going to be equal to this. Okay. So that's the basic computations. Once again, we stress that the mean and the marginal distributions do not in any way capture the essence of the process. You can have infinite variation of processes with the same mean. And typically in the rest of the course, we're going to be basically always systematically saying, let's suppose the process has mean 0, because it's not a loss of generality to suppose that your process has mean 0. From a mean 0, you can extrapolate any mean function simply by addition. So that's the mean function. I'm not going to ask you if there's any questions on this. If you have questions on this, if you have problems with the computations, please send me an email and we will discuss what needs to be done to help you out. Now, next definition is the definition of the autocovariance function. If you have a stochastic process, xt, which has finite variance at any stage, then the autocovariance function of this process is what? Well, is the function gamma, which depends on 2 entries, r and s, and this is given by the covariance of x, r, and xs. So the covariance function is, so definition 1.31. The covariance function or autocovariance function. So the autocovariance function, the auto in autocovariances just emphasizes the fact that you're taking the covariance, but of the process with respect to itself. But it's also just called covariance function. Its what is a function which depends on two time points, gamma of rs or gamma x of rs, and it's just the covariance of xt with xr with xs. And I suppose you all know the definition of the covariance. The covariance is the expectation of xt minus its mean. R not t. Multiplied by xs minus its mean. And this is equal to this. Are you all at ease with the green equality that I've done there?
Yes.
Yeah.
Okay. Once again, maybe you are not. If you're not, send me an email. We need to talk. Now, computations with autocovariance are. I mean, there is literally no fun in this. I mean, I like computations. There is no fun in this because it's relatively trivial. Computing with the autocovariance can be actually quite tricky. Let's have a look at example 1.32. So if we have an IID sequence, so if the xt's are IID, well then the autocovariance gamma of rs is what? Well, it's by definition the covariance, maybe I'll just write the word covariance. It's the covariance of xr and xs, and you have to get used to this kind of thing. We have to discuss in terms of what r and s do. So if an r is equal to s, well then that's just the variance of xr, which is just some sigma squared. And if r is different from s, then it's just 0. That's okay for everybody?
Yes.
Okay. If we take xt, which is defined as a function which is just one variable spread over all time points, well then gamma of rs is what? It's the covariance of xr with xs, which is just the variance of x for all rs. So this is constant over all time. If we take xt, if we take xt, which is of this form, no, I took with a z. So if we take xt, which is of this form, then gamma of rs is going to be covariance of square root of r z square root of s z, and that's what? Well, that's, and z is normal 0, 1. Then this is just going to be square root of r times s times the covariance of z with itself, which is just going to be square root of rs. So you see it's a very different function. This function here is very different from this one, and it's very different from this one. I guess that's still okay. You give me a shout if it's not. Okay? And then the last one is finally something a bit, well, not tricky, but a bit, well, you have to compute. So it's a times zt plus b times zt minus 1. We take the zt's, which are IID Gaussian, mu sigma squared. What's the covariance function in this case? Well, we need to look at it. So it's the covariance of azr plus bzr minus 1, azs plus bzs minus 1. Here I'm just going to use the bilinearities to get this. So it's a squared you give me a shout if I'm making a mistake. I think I've made no mistake so far. And now we need to discuss. So what are the different possibilities? Maybe somebody wants to help me out. No, I think I can do that myself. So we could take r is equal to s. If r is equal to s, then we have a squared plus b squared times sigma squared. Give me a shout if I'm wrong. If r is equal to s minus 1, then I will have ab times sigma squared. And if r minus 1 is equal to s, I will have the same thing. And otherwise, I have 0. Now this is more delicate. Does everybody see this? Or maybe I'm wrong. I think I'm correct. I'll just rewrite this a bit more efficiently. Is everybody happy with what I've done?
Yes.
Yes? Okay, so again now we have quite a nice function here. So in the IID case we had just a function which spiked at when r was equal to s. And well, this is a trivial case, we had something constant. In the case where we had a linear, well, we had a simple function of a single signal, then we had this relatively pretty but not so interesting function. And now here we have something which maybe I should write it like this. So if r minus s is equal to 0, then we have something. If r minus s is equal to 1, then we have something else. And if r minus s is larger than 1, then we have 0. Okay, so that's that. As I'm saying in the example, more examples will be tackled in the exercises. Now, in general, strict stationarity is too stringent. It's too often difficult, and it's too often too difficult to verify. I give you a general process. Well, then it's not hard to construct interesting processes which are not strict stationary. So rather than imposing conditions on all possible distributions of a time series, we will in general use a milder version of stationarity that only imposes conditions on the first two moments. So we're only going to be speaking of the first two moments of the series. And in the sequel, well, we will call stationary, we change the definition of stationary. So we don't, when we speak of strict stationarity, we mean what we meant by strict stationarity. But if we speak of stationary, what we mean in fact is weakly stationary, where weakly stationary is what? Well, it's what's in here. So the process is weak stationary if it has finite variance at all time points. If its mean function is constant, and if its covariance is shift invariant. So we saw just before, we saw that strict stationarity implied, so we saw it here, strict stationarity implies constant mean and implies shift invariance of the covariance function. Well, here we take this actually as a definition of a weak version of stationarity. We say that a process is weak stationary and therefore stationary if it has constant mean and if it has, well, in some sense, constant covariance function. So obviously, strict stationarity implies weak stationarity, but the reverse is not true. For example, we could consider the sequence here, which has different distributions according to the parity of the time. Well, that guy here, at every time xt, the mean is 1. Secondly, the covariance is, well, it's an independent sequence, so the covariance is going to be only non-zero at lag 0. Sorry, that's not a very good notation because I hadn't defined this yet. So this should be gamma x of t. T is 1 and gamma and this should be gamma x of ts with t different from s. That's better. So it is going to be weakly stationary, but it is not strict stationary because the distribution changes depending on the parity of t. So it's not hard to construct examples which are weakly stationary but not strictly stationary. So two examples which are important, which are stationary. Well, the first is the white noise. If you have a white noise sequence, then as we already seen, its mean is its mean is constant. The autocovariance is going to be given by this. That's what we did here. It's basically the same thing. Therefore, we have weak stationarity, but not all white noise is strictly stationary. It will be strictly stationary if it were. Yeah. Okay. If it were also IID or Gaussian, which would be equivalent. Another example where we have equivalence between strict stationarity and weak stationarity is the case of a Gaussian process. But here I'm just repeating the same thing. If we have, so in the case of a Gaussian process, independence is equivalent to absence of correlation. And that's basically what we're requiring when we're requiring weak stationarity. Okay. So I suggest we take a short break now. So it's 4:11. Let's say we start again at 4:20, if that's okay for all of you.
Yeah.